Today's topic is for loops. For loops. So if you can get ready to take some notes on more loop structures, we get started. Okay, so here's an example of a for loop. And again, this is like the other loop that we did. But remember, we were doing while loops and it had 3 different steps. Here, a for loop has 3 steps as well, or actually 4, but it's a lot more concise than a while loop. So in a for loop, if you take a look at the example, you start with a starting variable and then you have an ending condition that uses that starting variable, and then the third part of the for loop is the thing that occurs on the bottom. So if I were to draw this in a flow chart, what I would do is I'd first put a box, and this is I equals 0. So we're starting out at 0. That's that first part before the semicolon in the middle of the for loop. Now that only happens once up at the top of the loop. Next, we test the condition. Since we're doing a condition, we use the diamond symbol. And we say while I is less than or equal to n, which is the number of periods we're going to apply the interest for. So n must be defined outside of this code snippet. So you put a diamond there, and then you have the body of the loop, and this is where we do our calculations. First we calculate the interest. Next we calculate, or we add that interest to the balance. And now we're at the bottom of the loop, and what we need to do is the third part of that first line in the for loop, which is the incrementation of I. And then we go back up to the top of the loop and test the condition again. So you see a loop that looks like this in a flow chart. You have the initialization that happens only once. You test the condition. If the condition is true, you do these 2 things and you add 1 to I. Then you go back up to the top right after the initialization of the condition and you test the condition again. Now when the condition is true, you do the body of the loop, but if it's false, you continue on in your code. Okay? Now if you remember from last time, the flow chart for a while loop was exactly the same. There's no difference pictorially or even with the text. They're actually the same loop. So a for loop, if you look at it from a picture point of view, is no different than a while loop. So then the question is, well, why even have the for loop if you can do it with a while loop? It's a good question. Okay, so here's the syntax for a for statement. The 3 parts of the for statement are there: the initialization of the control variable, the conditional test of the control variable, and finally the update of the control variable. Now, what's the control variable here? It's going to be I. That controls how many times we go through this loop. I gets incremented closer and closer to n until it finally equals n and then goes 1 past it. Once it goes 1 past it, this condition fails and it goes on. The condition, or in this case I, is in all 3 parts. If you don't see I in all 3 parts, there's probably a problem with your for loop. There might be a few times where you don't have to put it, but most of the time if you don't see the control variable in all 3 parts, there's going to be a problem with that loop. Either it's going to go forever or it's never going to execute. So we're going to walk through this just quickly. First you initialize I to 1, so that's the first part. Then you test the condition. Is 1 less than the number of years? Let's say it is. So then we do the body of the loop, that's here. Finally, once we're done with the body, we need to increment I. So now I is equal to 2. And then we test it. Is 2 less than or equal to the number of years? So you can see the initialization of the control variable, the conditional test of the control variable, and then the change of the control variable. Control variable appears in all three parts. All right, so here's our example. We're going to start n out at 3, the balance at 1,000, and the rate as 10%. So we go into the for loop. First thing it does is initializes the condition, or initializes the control variable. Next, we do the test. So you see here the middle part. Try to see if this is true. Was I less than n? Well, I started out at 1, and n is 3. So yeah, that's true. So then we do our add interest part. So you calculate the interest, and then you add that interest to the balance. So you've got an extra $100 there. And you go back up to the top. This time you're incrementing the value of I. You see I now is set equal to 2. Go back up to the top. Here, I is less than n. Take a step. You add interest to the balance. The interest is 110. We add that to the balance. Now our balance is 1,210. We increment I one more time. We test to see if 3 is less than or equal to 3, and it is, so we go back up to the top. Do that one more time. Adding in the interest, we get $121. Now we're at $1,331. Take a step. Add 1. Now this time, you see that I is greater than n. So this test of the condition actually fails. So this is the terminating condition for the loop, and so out you go. And you execute the next line of code after the body of the loop. If you were to look at this in code, this is what it would look like. Here the investment is being created using a balance and an interest rate. Here's wait for balance. Here's wait years. You'll note that this one uses a while loop. The main reason for using a while loop rather than a for loop is that in a while loop, you're not exactly sure at the time you write the code how many times this is going to be, right? If the user says, I want to figure out what my balance will be, I want to see how long it will take my balance to get up to $20,000. Well, this piece of code will figure that out, but we don't know how many times we're going to go through the loop because the user could choose any target balance. So in this case, we have to use a while loop because we don't know exactly how many times the loop is going to go, nor can we calculate that. But in wait years, it's pretty obvious. They said how many years they want to loop. So in that case, when you know or can calculate the number of times you need to do the loop, it's more concise and probably better to use a for loop rather than a while loop. So this is a good example of when to use a for loop, when to use a while loop. Again, for loop, you can figure out how many times you're going to go through the loop, where in a while loop, kind of depends. We're not quite sure. So you use a while loop in that case. So if we were to rewrite the for loop and wait years into a while loop, which you can do, right? Because a for loop is just a specialized form of the while loop. What would that look like? Like this. Here, Now we don't use a for loop, so we have to do the initialization, the test, and the change of the control variable in 3 separate lines of code instead of 1 line of code. The body stays pretty much the same, apart from the change to the control variable. So anything you can do with a for loop, you can do with a while loop, but the other way it doesn't work. Not every while loop can be turned into a for loop. And the main difference is the number of times you go through the loop is not known and can't be known when you write the code. Here's one. This one catches people all the time. How many times does the following loop execute? You start I at 0, you say I less than or equal to 10, and then I plus plus. Well, the values of I will be from 0 to 10, but how many times is that through the loop? It's kind of deceptive. Because we said less than or equal to 10, and we said I starts out at 0, this is actually going to happen 11 times. Because you'll get to the first time will be 0, the second time will be 1. Okay, so you're off by 1 there. That's the value of I, right? So you start out with I equaling 0, and then you print out I times I, which is 0. So you go through this loop 11 times. Now if we were to take away the equals and just make it less than in the condition that has the control variable in it right here, if we just took away that equal sign, then it would only happen 10 times. Because as soon as you get to 10, well, 10 is not less than 10, so it would condition would fail. But you actually get 11 times through the loop. This is called an off by 1 error, and this happens a lot for programmers that don't pay attention so much to the detail, and they realize, oh, geez, I'm doing this too many times. But very common problem. The thing that defines how many times you go through the loop is the control variable. Here it starts at 0. And then also this relational operator. If you see an equal sign, then you really have to think about what are my boundary conditions on this loop. All right, so here's some examples on a for loop. The first one is you go from 0 to 5. How many times do you go through the loop? 6 times, just like our previous example. So here's the values of I. So you end up going 6 times because we start out at 0. Here we start at 5. We're going down to 0. We still have 6 iterations, but right here, notice that we're subtracting from I so that we can count backwards. Say you want to change I by 2 instead of 1. You don't have to just increment by 1. You can change I lots of different ways. So here we're going from 0, I is less than 9. So we start out at 0, 2, 4, 6, 8. Finally we get to 10. 10 is not less than 9. So the loop ends at that point. So this is what you see for the values of I. This one is kind of tricky, and I see this happen a lot. You have your for loop. You're trying to test if I is not equal to 9. So you want to stop when I is not equal to 9. Well, we start out at 0, then we add 2, and add 2. We get to 8, then we add 2 and we get to 10. Well, you'll note that I is never equal to 9. So unfortunately, this creates an infinite loop and your program stops working, or keeps working and it doesn't respond to user input. The reason is because the value of I is never going to be 9. The value of I will be all the even numbers from 0 to whatever, but it'll never be 9. So this loop will never terminate. Here's another one. In this case, we're doubling it each time we go through the loop. We only want to loop while it's less than 20, so we got 1, 2, 4, 8, 16. When we get to 32, it terminates the loop. So these are all powers of 2. Now if you're a computer programmer, you probably need to kind of have in your head the powers of 2, because again, the computer is a binary machine. So what are the powers of 2? Well, it's 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. That's about where I stop. Okay. So why do software engineers and computer programmers have that in their head? Is because, again, we program computers all day. Those numbers come up all the time, right? How many megabytes do you have? 8 megabytes. How many gigabytes are on your hard drive? You know, gigabytes is 1024 megabytes. So again, all powers of 2. Finally, the last one, say you want to go through a string, a character at a time. Say you're doing a crossword puzzle, or maybe Scrabble, a computer version of Scrabble. You can actually ask the string how long it is and use that in conjunction with here to get that character at that position in the string. So it would go until you run out of string, I guess, and then this loop would stop. So it allows you to go and take a string and parse it character by character. Okay, so let's look at some common errors when it comes to loops. So here we have a missing semicolon. Remember, the 3 parts of a for loop or for statement are separated by semicolons. So here's the initialization. You see that there. Here's the test of the condition, which is kind of weird because you're doing all this math inside it. What's missing over here is the semicolon before the update of the control variable. So to fix that, you would put a semicolon there. Here's one. This is really common too. I see this with if statements and also with loops, is since most everything in Java you have to put a semicolon in the end, one of the few places where you don't is a for loop, also a while loop, or an if statement. Because the statement is actually, this is what you're trying to control with the loop, is this accumulation of the sum. But since you put a semicolon there, the loop will do 10 times of nothing and then just do the sum one time, because you cut off the for statement too early. So the way to fix this is to take that out. Then this will be controlled by the loop, and then you'll actually get the sum. All right, so this next series of slides, we're talking about some of the things you normally do with loops. These are things where if you've been coding as long as I have, you see these all the time. So it's good to talk about these common loop algorithms that help you figure stuff out. This first one is you're trying to sum up or compute a total. You have a list of numbers and you want to add them all together. Say these are all your sales for the day. So here we're doing a running total where the user is going to type in a bunch of numbers. Say this is a cash register point of sale device, and it's reading the numbers perhaps in from the scanner, the barcode scanner on the device. So you say this, while in has next double. So what you're doing is you're checking to see if there's something. You haven't read it yet, but you want to see if something's in line to be processed next. So the computer will look in its buffer and say, do I have a double there? If it does, it'll go in the bottom of the loop and we'll grab that double, calling next double, store that in input, and then add that input to the total. When we started, total was initialized to 0. So as long as it has another double coming in the queue, it'll add that to the overall total. So this is a very common algorithm for totaling things up. I used to write report generators where I have to total up, say a company's got like $3 million in sales. I had to create reports that would go into their accounting system and build that report for them. And so I had these things called accumulators. And that's what I was doing, is I was just accumulating all this data and presented it on a report for the mucky mucks to take a look at. Here's another one. You're trying to find perhaps a specific character. Say you want to count up the number of capital letters in a string. So we're counting up matches. So this is called counting matches. We initialize uppercase letters to 0. And then we're going to go through the string one character at a time and see whether or not that letter is a capital letter. So we start out at 0 because the position numbers in a string start out at 0, not 1. And then you say this, okay, go into the string and get the character at position 0. If that's an uppercase, then add 1 to our count. If it's not uppercase, then don't. So there's no else part here. It just doesn't do anything. So this will go through the entire string, including spaces, and test whether it's an uppercase letter or not. If it is, it adds 1 to our count. Later on in the code, you would perhaps put that up on the screen and let them know how many capital letters there are. So again, this algorithm is called counting matches. Say you want to find the first match. You don't want to count them up. You just want to find it. And again, all these are in the book. But first, you set a Boolean variable to false, saying you haven't found it yet. Say you're looking for a question mark. And you want to stop or figure out where that question mark is in the string. So you say, and this is kind of weird, you say, while not found, say, while you haven't found it yet, and the position is less than the length, if those two things are true, then do the body of a loop. If either one of those is false, then you leave. You're either at the end of the string or you found it. If you're at the end of the string, well, we're one past the end of the string and you didn't find it, you want to stop, right? Because you don't want an infinite loop. So here you have a compound condition where you have this, which is a Boolean, this is a Boolean, and then we have this Boolean operator, and. So 2 ampersands means and. So if it's not found and the position is somewhere in the string, then go and get that character, test to see if our character is, we try to see if the character is lowercase this time. If we find a lowercase letter, then we set found equal to true. And we go back up to the top. Now that we found it, while not found, well, found is true, so not found would create false. Since that's false, then the condition will evaluate to false, and you'll skip the rest of the body. So what you have at the end there is the position now will hold the location of the lowercase letter, the first lowercase letter that's in the string. So again, the algorithm finding the first match. Here's one where you're asking for a specific item. Typically, this is a good one to use for passwords. Okay, so here you set valid equal to false. You have this double, which is called input. And while it's not valid, so not false is true, okay? Or not valid is true. Then you go here, say enter a positive value less than 100. The user types in the next one on the input stream and say, well, we said it has to be positive, so here input needs to be greater than 0 and input needs to be less than 100. If both of those things are true, then you set valid equal to true. And then when you go up to the top of the loop, it'll let you out of the loop. But say they put in 100. Well, 100 is not less than 100. It is greater than 0, but it's not less than 100. So you do the else part, and you say invalid input. And the loop would continue. So you're sitting there looping, waiting for the user to put in a valid piece of data. So this is called a validation loop, or prompting till a match is found. The one I like better is like a password. The user, you say type in your password, they type in the password, it's the wrong password. So you don't let them continue on in the code. You use them back to the top, say no, that's not a correct password, please enter the password. And so they're going to be stuck in this loop until they enter the correct password. And that's what you want. In most cases when you have a password, you want to make sure that they only get in unless they only get in knowing the password. If they don't know the password, they don't get in. Here's another one where you have two numbers that are right next to each other. So you have this list of input coming in the input stream. You read in the first one, and then while there's another one in the list, what you do is you get the input, the first one, and compare it to the previous one. And what you're trying to do is looking for adjacent duplicates. So you take the input and store that in previous, and then you go and get the next number. So you've read in this one and now the 7. And if the input is equal to the previous one, then you say, hey, there's a duplicate input. Otherwise, you keep going. So the next time through, this will be previous, this will be the current one. Those aren't the same. Go around the loop again. Here now we're at this one and this one. Those aren't the same, so you go around again. Finally, you're at the 9, the first 9, and you read the next line, and then you compare them. You get 9, is 9 equal to 9? And the answer is yes, so then it prints out duplicate input. Now, if there is no duplicate input in the stream of numbers, then the program doesn't print out anything. So this is how to look for values that are the same right next to each other. Here's another one where you process input that has a Sentinel value in it. And what a Sentinel is it's like a gatekeeper, okay? Kind of need to look at the example to see it. So Sentinel value sometimes can be telling you that you're done with the input. A lot of people use a -1. If you have a whole bunch of integers, positive integers, and you want to stop when it at a certain point, you put a special value inside your data that will stop the program from executing. Now, it says 0 and -1 make poor Sentinel values. It's better to use Q. So you tell them to say, enter a value, or type in Q to quit. First thing we do is we get the next thing. Remember, the next thing might be a number. So we get that next thing. If it's a Q, then we're done and we exit the program. Otherwise, we take that input we read in, parse it into a double, and store that next. So here, we're limiting access into our loop based upon a Sentinel value. What's odd here is this isn't a loop, so I'm not sure why this slide is in there. Here's a common loop algorithm, and you're looking at it and there's no loop there. So some poor editing when it comes to the slides. Yeah, so the loop is missing from the slide for some reason. Here's another one called loop and a half. There are better ways to do this, so we're going to skip this slide. Okay, so here we have a data analyzer, and we're using the scanner, and we're setting the scanner. Remember, the scanner is this thing that allows us to read data in from a file or from the user. In this case, we're reading it in from the user, the command line. Create the new scanner. We create something called a data set. And then we start our loop. We set done to false because we're not done yet. While we're not done, then we say enter a value or Q to quit. Notice they did this right in the code. So what they forgot on the previous slide was the loop right here. So this slide is faulty. But anyway, they have a good example here. So while not equals done, or while it's not done, then you ask them for the next thing. Now, note here where it says in.next, we're not sure if that's going to be a letter or a number. So we don't say next double or next string. What do we do? What we do is just say next. Okay? So right here, let's see, right there. Valid inputs are either a double, like a number, or the letter Q, which is a string, or which is a character. So at this point where we read it in, we're not quite sure what it is. Is it a string or is it a number? We don't know yet. So we take that input and compare it to the letter Q. If it is Q, then we set the done flag to true. This else part doesn't get executed. We go back up to the top. Now done equals true, so not done is false. That stops our loop, and we go on. So right there, that's the generic form of next, when you're not quite sure the data type you're going to be reading next. In this case, is it a letter or is it a number? So first we test the Sentinel value. If it is correct, then we say, okay, we're done. Otherwise, well, it must be a number then. So we're going to take that input, parse it into a double, and then store that next. Finally, we take that number we read in and we add it to our data set. Interesting. And then our data set, we can ask it, okay, can you take all the numbers inside you and get the average number, right? Or say we want the maximum number. Now, our assignment in the chapter is we're trying to figure out the maximum temperature. So this would be a good one to look at for that, if you'd like to see that. Here's our data set class. We have the sum, we have the maximum, we have the count. With the sum and the count, we can figure out the average, right? So here's our data set. We initialize everything to 0, the 3 instance variables. When we say add, we have some value coming in. We add that to the sum. And in the special case where the count is 0 or the maximum is less than x, then we set the maximum to x. And then we increment count. So we're not storing the numbers, yeah. The data set? Yeah, you can use this to do the temperature thing. Yeah, it's in the book. I don't know if they do that. Let's see. But this would be a good way to do it. Yeah, it looks like in our example it's not using the data set, but you're certainly welcome to. You could use that. The code on step 7, you note if you look at it on page 218, it's not using the data set. Of course, it's only looking for the highest value, but if you want to give yourself a little bit more information, let's say you don't want to know exactly what the sum of or the largest temperature is, but you also like to know the average temperature, which would make sense since it's temperatures. Then you could ask that question if you store your values in the data set. So that's a good point. So if you want some extra credit, you could implement the how-to on page 215 as using the data set rather than what they recommended in the how-to. What's nice here is you have all the code and it's commented. So you could utilize this data set. You just keep adding numbers to it, and then when you're done, you ask it, okay, go out and get the average, gives you the average temperature, and then if you want the sum, how do you get the sum? Don't want the sum, but we want to get the maximum. So this data set doesn't have a get maximum, so you'd have to add a get highest method, and that would be an accessor method, which will just return back the maximum. So you're missing one method that you might need to do the assignment, but at least the code is there. There it is, get maximum. And all you do is return the maximum. Because you remember, every time we put a number in, it's doing the math to figure if is this the highest one? If it is, I'm going to reset maximum so that when the user asks for the maximum, it'll be there. So yeah, why don't, if you want to get a little extra credit, that'd be a good way to do it, is use the data set to store your temperatures so that we can ask for the average temperature as well. So suppose you run this program, you put in a 10, you put in a 0, you put in a -1. Then they type quit because they've run out of data, right? So you need to tell the program using a Sentinel value, hey, I want to stop. So it stops. Computes the average. Well, it's already computed the average as you went. I guess not. It'll take the total, divide it by the count, and that gives you that. So what do we get here? We got 9. 9 divided by 3 gives us 3, so that's correct. What's the maximum number we put in? We kept track of that as we were putting them in, so we know that the maximum number is 10. So again, that's very similar to what we're doing in How To 6.1. Here's a few more self-checks. I know this is a long lecture. I apologize for the length. So how do you compute the total of all positive inputs? Well, you could do it this way. You start out 0 for the total. You get the next double. Well, you check to see if there is a next double. If there is, you go get it. Store that in input. And if the value that you read in yeah, so this is incorrect, this slide. Let me fix the slide. This should say, yeah, that's what it should look like. So you check to see if it has the next double. If there is, you read it in, store it in input. If input is greater than 0, meaning it's positive, then you do this part. You add the input to the total, and you reset the value of total. And that will only add in positive numbers, but not negative ones. So if you remember back on the previous slide where they talk about comparing adjacent value, what happened if no input was provided at all? Okay, so the user didn't put anything in. Yeah, so the initial call to in.next double fails, terminating the program. One solution is to do all the input in the loop and introduce a Boolean variable that checks whether or not the loop is entered for the first time. So yeah, it's a mess. I wouldn't worry about that, but we haven't really learned how to handle errors yet. Let's see if we can get to that. Here's the question I had, remember from the previous slide. Why does the data analyzer class in.next call in.next and not next double? Because we don't know whether the input is a number or the letter Q. So we have to use the more generic call, which is next. Would the dataset class still compute the correct maximum if you simplified the update of the maximum field in the add method to the following statement? If maximum is less than x, then maximum equals x. Would that work? Seems plausible. It says no. If all input values are negative, the maximum is also negative. However, the maximum field is initialized to 0 with this simplification. The maximum would be falsely computed as 0. Yeah, because if you look back at the loop, let's go look at that loop. Yeah, see here in the constructor, we set maximum to 0, even though it's not the maximum. So if you put in just negative numbers, it would report back that 0 is the highest number, and it really wasn't.